within the enterprise offices. Finally, we will look at the increased use of wide area networking, concentrating on the main technologies deployed in today's data communication networks. The year is 1840. You are traveling across the open prairies. Scanning the scene, you notice large puffs of smoke rising from one of the highest points around. You wait, wondering what to do next. Almost simultaneously, you notice similar smoke rising from hills to your left. The events continue, first a string to your right, then to your left. Straining your eyes and shading them from the sun, you notice people gathered around the fire. Suddenly you realize that these people are sending messages. The streams of smoke are a code, and the code is understood by the people on the other hill. What you have witnessed is the American Indians' long-distance communication system. Similar systems have been developed around the world for centuries. African drums, Greek helioscopes, and British naval flag systems. They all have the integral parts of a modern-day communication system. Transmission is through the air. Geographic limits are as far as the eye can see. They have an information carrier. They have a code, they have a transmitter, and a receiver. Until the invention of electricity, these were the best available communication systems and were limited by line of sight. In the 1830s, an American, Samuel Morse, invented the electrical telegraph, and the age of long-distance data communications was born. In its simplest form, the telegraph is just the making and breaking of an electrical circuit. Coupled with the development of the Morse code, which represented letters with two types of electrical pulses, a full communication system was available. By the 1870s, telegraph was international. By the 20th century, the operator was equipped with a teleprinter, which considerably improved the speed of data input and output. The age of global data communications was born. Further improvements in data communications were necessitated by the widespread use of electronic computers, which were introduced in the 1950s. Early computers used punch card for input and printers for output. There was little data communications in these systems, as all devices were located in the same room. Communication was via short pieces of cable. Computing was most often accomplished via batches. Programs would be loaded one day, processed overnight, and output the next. The 1960s saw the growth of online processing. The development of the computer terminal allowed direct input of information into the computer via keyboard and screen. Most terminals were still located close to the computer and could connect over slow serial links running over long cables. The 1970s saw the first real long-distance data communications between computers. Employees now wanted to communicate with the mainframe computer from other offices or branches. Access to database and accounting information was particularly important in the insurance and finance industries. Computer manufacturers such as IBM, Data General, and DEC began to develop data networking systems to allow remote users to access the information on the mainframe. However, to ensure security and control over the valuable information asset, all communication was controlled from the center. These computer environments were called host terminal systems and were the mainstay of corporate computing until the 1980s. In the 50s to the 70s, businesses were hierarchically organized. This was mirrored in the hierarchical structure of their IT systems, typified by various host terminal architectures, such as IBM's SNA, which was born in 1973. These architectures were proprietary and very poor at integrating disparate systems, so such integration was avoided, leading to one-vendor shops. In the 80s, the fashion was for decentralized structures. At the same time, the arrival of the Mini, the PC, and the LAN enabled newly independent business units to go it alone with their own IT platforms. Control and distribution of information was often hard, as multiple systems were introduced. The 1990s has seen the growth of the client-server architecture. Again, built on PCs, minis, now called servers, and LANs, the client-server architecture adds order to the flow and storage of information in distributed systems. In a true client-server network, a server holds all the programs and databases, enabling a user to log on to the server. The applications are then downloaded to the client, user's PC, from the server. There are a number of advantages associated with a client-server architecture. Firstly, the client users do not need as powerful a computer system as the work is done by the server. It is also easier to manage the system, and the server database is the only device that needs regular backing up. Finally, the system is usually less expensive than alternative architectures, where equipment and software is dedicated to a particular user. The largest example of a client-server architecture is the World Wide Web. Communication using data is very different to communication using voice. In this section, we will look at these differences. We will also define some of the basic terminology used within data communications. In particular, we will introduce the concept of a communications protocol. Computers are digital devices. That is, they always think in zeros and ones. Information is processed and stored in a series of zeros and ones. A single information unit of 1, 0 or 1 is called a bit. To represent everyday information, computers combine bits into multiples of 8. In this system, 8 bits is called a byte. A byte can have 2 to the power of 8, or 256 unique sequences of ones and zeros, and these are used to represent written letters, numbers and symbols. The same is true when computers communicate. The ones and zeros need to be replicated in the communications system. This is called a two-state communications system. The most simple form of such is still the basic telegraph system invented by Morse, but the process is the same in the most advanced data communication systems available today. There are many types of dialogue possible with human speech. The same is true for computers. With computers, there are 3 basic forms. Simplex mode. In simplex mode, communication is actually a monologue with one device transmitting and the other receiving. To get a picture of this, think of the telegraph machine's form of communication. Dot 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 dot, dash dash, dot dot, dash 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 dash, dot dot dot, dash dash. Half duplex mode. When in half duplex mode, computers take turns transmitting and receiving, the computer equivalent of talking on a speakerphone. Some of us have experienced proper conversational etiquette being forced upon us by the unique speakerphone phenomenon of forbidden interruption. The speakerphone mechanism dictates that you may indeed speak your mind, but you'll have to wait until the other end stops first. This is how computers communicate when in half duplex mode. Full duplex. With full duplex, the only conversational proviso is flow control. This mitigates the problem of possible differences in operating speed of the two computers, where one may be transmitting faster than the other can receive. Other than that, communication between the two flows unregulated, with both sides transmitting and receiving simultaneously. If an English speaker wants to make a telephone call to a person in Italy, the telephone network will establish the connection. All the sender needs is the address. However, if the receiver can only speak Italian, then even though the communication path has been established, communication will still not take place. The same is true with computers. A protocol is an agreed set of rules to allow communication to take place between computer systems. Protocols provide a number of advantages for delivering data. In most cases, guaranteed data delivery end-to-end. They can report to the user if there is a problem, and if an error does occur during transmission, then the protocol can recover the lost data. This process is an invisible operation as far as the user is concerned. In In the 1970s and 80s, each computer manufacturer developed their own communications protocols. Only devices from that manufacturer would understand the protocol. Customers became locked into single vendor architecture. As these protocols became more and more complex, the development and maintenance began to produce support issues. In the early 1980s, the International Organization for Standards, ISO, developed the Open Standards Interconnection, OSI, model. The idea of the model was to break down the communications process into discrete functions, thus allowing multi-vendor interworking and assistance in speedy development and support. The OSI model defines a 7-layered architecture. The protocols defined in each layer are responsible for communicating with the same peer protocol layer in the opposite computer and providing services to the layer above it, except for the top application layer, of course. Obviously, each layer does not have a physical wire running between it and its peer layer in the opposite system. To send a message, a protocol must put the message in a packet and pass it down to the next lower layer. Thus, the lower layers provide a service to the higher layers by taking their messages and passing them down the protocol stack to the lowest layer, where the messages are transferred across the physical link. The OSI defined the general functions of each layer, but not the actual protocol. However, this model provides a particularly useful reference point when discussing more specific protocols later in this module. For future discussions of data communication services, the lowest 4 layers are of the most importance. For example, SDH, used in leased line products, is a physical Layer 1 protocol, whereas Frame Relay defines protocols at both the physical and data link layers of the OSI model. Unlike computers, human beings communicate via voice. Voice is an analog, continuous variable wave form of communications, with information transmitted via different frequency waves. Telephones will convert sound pressure waves into an electrical analog signal, microphone, and electrical signals into sound pressure waves, speaker. The frequency range for speech on an analog circuit is 300 to 3400 Hz. Speech being carried through an analog circuit is also called 3.1K speech or commercial speech. The original telecommunications network was designed to carry these voice signals. As already indicated, digital signals operate on the presence or absence of electrical pulses, i.e. pulse or no pulse, quite simply on or off. Every calculation is done using this two-state or binary system. These digital signals will not fit over the analog voice network without conversion. For the last 30 years, most telecommunications service companies have been upgrading their networks with digital switching and transmission. In these systems, voice is now transformed into a digital signal via a device called a codec. The word codec comes from the words coder and decoder. The encoding technique generally used is called pulse code modulation, or PCM. PCM works by sampling the analog signal 8,000 times a second, taking the sample and then converting it into an 8-bit digital code, then finally transmitting the 8-bit code 8,000 times per second. It is from this process that we get the standard digital voice channel transmission rate of 64 kilobits per second. Bandwidth is a measure of the difference between the highest and lowest frequencies available in a communications channel. Bandwidth is often used to refer to the throughput of a digital data transmission system, but it is only indirectly related to throughput. The data transfer rate is a measure of the amount of digital information that can be transmitted through a channel per second. Data transfer rates are also referred to as throughput rates. A number of factors determine data transfer rates, including bandwidth of the line, transmission impairments, distance, and media type. The bit rate of a channel is the bits that can pass a point in 1 second. For example, with a 1 megabit per second line, 1 million bits can pass into the line per second. Hence, the more bits per second, the faster the line. The 1 megabyte file of this presentation would take 8 seconds to be transferred on a 1 megabit per second link, but would take only 0.8 seconds on a 10 megabits per second Ethernet LAN. Remember that a byte is 8 bits. Therefore, a 1 megabyte file contains 8 million bits. Modems, modulator-demodulators, are data communications devices that allow two computers to communicate over the public switched telephone network. A modem at the sending computer converts computer digital signals into analog signals that can be transmitted over the telephone lines. A modem at the other end of the link reconverts the analog signals back into digital signals. There are many modulation standards available for modems. Most are provided by the International Telecommunications Union, ITU, which means that modems from different manufacturers can be used at either end of the link. Speeds supported also vary with the modulation technique used. The slowest and oldest modems operate at speeds of 1,200 bits per second, whilst the latest V90 modems operate at speeds of up to 56 kilobits per second. Until recently, modems were considered as going out of fashion, as newer and faster digital data communications methods have been deployed. The recent growth in mobile working and the phenomenal growth of the Internet has given modem and modem technology a new lease of life. In today's digital voice networks, it seems strange to take a digital signal, convert it to analog, then send it to the telephone network, have the telephone network convert it back to digital, then transmit it to the other end, and finally convert it all back again. However, for some users, such as mobile or small office users, they are still an economic solution. We will see later how the advent of Integrated Service Digital Network, ISDN, overcomes this issue in using devices that can be considered as being digital modems. We will now look at the technology deployed to interconnect computers within buildings. This technology, known as a local area network, is of particular importance as applications running over LANs produce much of the traffic that is carried over national and international data communications services, such as frame relay, ATM, and private circuits. We will specifically look at the common LAN technologies of Ethernet and Token Ring, which are now deployed in the majority of medium and large organizations worldwide. Finally, we will look at the growth of interconnected LAN networks and the development of internetworking devices such as bridges and routers. You will also be introduced to the most important data communications protocol in use today, Transmission Control Protocol, Internet Protocol, TCP/IP, which is at the heart of the Internet. In the 1990s, the need to connect a variety of equipment within the local workplace has become essential. The workplace is a breeding ground for high-technology equipment and software that assists us in carrying out our daily tasks, such as computer systems, laser printers, plotters, terminals, word processors, electronic mail, and personal computers. We depend on our machines to be able to communicate quickly and easily. They also give us access to powerful shared resources, such as database and file systems. What is needed is a method of networking all these devices so that everyone can share critical information and resources. This reduces complexity in the office, improves efficiency, and reduces office costs. Information is usually transmitted between devices in the office via a local area network, or LAN. A LAN is a high-speed information transport system operating among a number of devices that are located in a limited geographical area, providing shared use of resources. This could mean a single department office, a large building, or a multi-building site or campus. Because most information exchange takes place in the local environment, it tends to be fast and of short duration, often called bursts of data. Once a LAN has been established, in other words, the wires and equipment installed, the ongoing cost of operation of a LAN is minimal. Often it is said that the bandwidth used by a LAN is free. Hence, most LANs have been designed based on the assumption that bandwidth is free. This has significant impact when we look at interconnecting LANs outside their limited geographical area, where bandwidth is no longer free. There are two main types of LAN used in data communications today: Ethernet, which has become the dominant type, and token ring. Originally proposed by Xerox in 1970, Ethernet has now been adopted by the Institute of Electrical and Electronic Engineers as the IEEE 802.3 standard. This is the most common LAN technology deployed today. Ethernet can be a bus structure that allows multiple devices to be connected to the same cable. It allows all the devices to communicate on the same link, but only one device can be transmitting at any one time. Data is transmitted between devices in frames. This information is broadcast onto the bus, but only the receiving station will recover the information. If two or more devices try to transmit at the same time, then a collision will result. Ethernet deploys a mechanism to prevent these collisions occurring. This is known as Carrier Sense Multiple Access Collision Detection, known as CSMA-CD. In this system, all stations listen to detect the bus is free and then transmit. If two stations transmit together, this is detected. Both stop transmitting and wait a variable length of time, known as backoff, and then try again. Information is broadcast onto the Ethernet LAN. Stations look at all traffic as it passes them and only react to messages that are addressed to themselves. An area over which broadcast traffic is carried is called a broadcast domain. Ethernet operates over a number of physical media, from twisted pair cable to fiber optic cable. Originally designed to operate at 10 megabits per second, the standard has now been raised so that Ethernet can operate at speeds in excess of a gigabit, 1000 megabits per second. The bus architecture of early Ethernet created a number of problems. The number of devices that could be added to a single broadcast domain was limited. Also, a break in the cable meant the whole LAN would not operate. Hence, a new version of Ethernet LANs was devised, built around a new device known as a hub. The hub provides a single cable to each device and then interconnects them to make them look like a bus. In this simplest form, all devices are still part of a single broadcast domain, so the number of devices is still limited. Later hubs also undertake what is called switching. With switching hubs, each port acts like its own LAN. Communication between ports is undertaken via the hub's switching capability. This also now allows ports to operate at different speeds. For example, a heavily used server can be connected on its own 100 megabits per second Ethernet, while individual users still connect on 10 megabits per second dedicated connections. Ethernet installations based on switched hubs are now the most common in large corporate customers. Originally proposed by IBM in the mid-1980s, Token Ring has now been adopted by the Institute of Electrical and Electronic Engineers as IEEE 802.5 standard. Token Ring has two speeds, 4 and 16 megabits per second. Physically, the network looks like a star network, with passive and active units used to provide interconnection. Logically, the operation is more like a ring configuration. Token Ring is a mechanism whereby each node, in logical order, receives and passes the right to use the LAN. A token is a special bit pattern that circulates around the ring from device to device. Only when a device has the token can it transmit data. When a device transmits a message, it will retain the token and send its message to the receiving device. When it has finished, it passes the token on. Never as widely deployed as Ethernet, it is now losing market share to Ethernet, even in traditional IBM computing environments. Devices are required that provide connectivity from, say, a personal computer in one network to a server in a different network. The computer may be Ethernet-based and the server token ring-based. The computer may be 1,000 kilometers away from the server. There are many scenarios where we require connectivity between devices in different and often disparate networks. For example, a bank may hold detailed records on its customers at head office, but these must be accessed by employees in their branches. Or a drug manufacturer may undertake development in multiple countries using a virtual team that constantly share information. Internetworking is the process of connecting such networks. Internetworking components are devices that offer connectivity services. In fact, any device that connects more than one network is referred to as an internetworking device. There are two main internetworking components used widely in public and private networks. The bridge, which can provide basic internetworking using procedures and protocols found in the data link protocol layer of the OSI model. The router, which can provide elaborate internetworking using procedures and protocols found in the network protocol layer of the OSI model. The bridge and router offer the same basic service, but in a very different manner. The router is the more flexible device, but it can only operate with protocols that have a network layer, TCP IP, Novell. These protocols are said to be routable. For protocol environments that do not have a network layer service, NetBIOS, NetBEUI, these protocols are said to be non-routable. If the protocol is non-routable, or if only a basic internetworking service is all that is required, then the bridge is the internetworking component of choice. A bridge is a LAN connection device with two or more ports that forwards frames from one LAN segment to another. The bridge can also offer connectivity between remote sites. Any elements connecting to one side of a bridge form a completely separate network to the elements connected to the other side of the bridge. The bridge, by nature of its operation, creates multiple logical networks. Any traffic transmitted on one side of the bridge will propagate to devices connected to that network. The traffic will arrive at the bridge as it is considered part of the LAN. The bridge, using address tables, will then decide if devices are connected to the same side of the bridge. If they are, the data is dumped, often called filtered out. If the bridge decides that the data is destined for a device connected to one of its other ports or interfaces, the other side of the bridge in other words, it will pass the data, or forward it, to the appropriate port. Therefore, we can state that only traffic destined for a remote device connected to the other side of the bridge will cross the bridge. The operation of the bridge is not essentially complex. The bridge will initially receive a frame of data on a port, take the source address, and build a source address table for that port. For any subsequent traffic received, the destination address is analyzed and compared to entries in the table. If there is a match and the address is on another LAN, then the traffic is forwarded to that port which connects to the LAN. Bridges can operate in between LANs located in one location. These are known as local bridges, or they can operate between LANs located in different locations. These are known as remote bridges. Bridges operate at the lowest layers of the 7-layer OSI model. They understand the media access control, or MAC, frame, and its fields that are found in both Ethernet and token ring LANs. This is an OSI Layer 2 data link protocol. The bridges can aid in preventing congestion, providing security, and generally increasing user response times if they are sited correctly. They can provide filtering of traffic between LAN segments and across remote links. Routing is the act of moving information across an internetwork from source to destination. This process may involve the information flowing across a number of discrete networks, often called subnetworks. These may be owned and operated by different organizations, as is the case with the Internet. Routers are interworking devices that undertake the task of routing. The basic task of the router is simple: to provide connectivity between devices in one network with devices in a different network. As a device that connects remote networks, the router offers a wide range of interfaces. The router is capable of selecting the most suitable line over which to send the data. This is controlled by routing tables that the router builds using their own information exchange protocol. The router then transports the information from the source computer to the destination computer over LAN and WAN interfaces. To complete this task, the router undertakes a number of tasks. Firstly, the router receives data on one interface. The router then looks at the destination address of the data packet supplied in the network layer header. It then performs a lookup in a table called the routing table, which tells the router which interface to use next. Finally, it sends the data packet out of the chosen port to continue its journey to the remote machine. The router operates at layer 3 of the OSI protocol stack and utilizes the information found in the network layer to provide its services. The router offers interconnection between LANs where a suitable route is selected rather than simply making a forwarding decision. The router therefore offers great advantage in functionality, requiring more processing power than a bridge. To successfully route a packet through the internetwork, a router must determine the packet's path. Let us look at an example of how a routing network achieves this. Assuming that device 6 of network 1 wishes to pass data to device 4 of network 3, device 6 will generate a network layer packet. The packet will be placed on the LAN in MAC frames. These will be addressed to the local router. The router will then examine the network address of the packet to determine which path the data should take. As shown, its routing table instructs the router to pass the packet out on port 2, encased in whatever wide area network WAN protocol is used. Routers can support complex network architectures. In this example, the router has two different WAN links to choose from. In real networks, the choice is likely to be more complex. From an economics point of view, a bridge tends to operate between LAN segments on a point-to-point link basis. Routers tend to interconnect fully meshed networks and provide features to maximize the traffic utilization of expensive WAN facilities. On arrival at the router local to network 3, that router will examine the network address and determine that the destination device is a local machine. The router will send the packet out on its local port, where it arrives at device 4. The packet will be encapsulated in the appropriate LAN frame for the LAN technology of network 3. Hence, the LANs on either side of a routed network do not need to be the same type as they do in a bridged network. For example, the device 6 may be attached via a token ring LAN, whilst device 4 may be connected via an Ethernet LAN. Routing tables are maintained by routing protocols transmitted between routers. These are complex processors that are beyond the scope of this module. Throughout the rest of these training modules, we will use the generic symbol for a router to indicate a router device. TCP/IP, and particularly IP, is the internetworking protocol. It is used extensively in the Internet and also in many private internetworking networks. TCP is a connection-oriented protocol operating end-to-end. Before information can be exchanged, the TCP layer has to establish a logical connection between the two end systems. Once established, TCP is responsible for getting information ready to transmit, and once transmitted, that it is received without error and in the correct order. To make this happen, TCP implements sequencing of messages, acknowledgements, error detection, retransmission, and procedures for dealing with drastic errors such as one device crashing. IP provides a universal way of packaging information for delivery across network boundaries. IP packets contain the necessary addressing information used by the routers to route information across internetworks. IP can be carried in almost any data link protocol, including Ethernet, token ring, ATM, frame relay, X25, and PPP. IP transfers all information in what are called IP datagrams. These are very much like the letters in the postal service. Each has an address at the destination. Once posted, the actual path taken to deliver the envelope may vary, and the actual method of transport, postman, bicycle, van, train or aeroplane, can also vary. This process is called connectionless. There is no pre-configured path down which the IP datagrams will flow. The new internetworking traffic generated from distributed LAN-based applications tends to have a bursty profile. A burst is a period of extreme activity on a communications link. This can be caused by two users exchanging a large file. In the past, I'm sure you have emailed a colleague and attached a very large presentation. A user making a remote inquiry of a database located on a server, or an email server exchanging the latest emails with the internet. When designing an internetworking network, this is not a significant problem in the LAN. If bursts are causing performance issues, then you can always upgrade the speed of the LAN, or the LAN connection for the specific user. Remember that the bandwidth of the LAN, the actual cables, can be considered free once installed. This is not the case over the wide area. Bandwidth is expensive. If the network manager were to size his internetworking WAN links to accommodate the peak burst traffic, then a significant amount of expensive bandwidth would be wasted. This would lead to an uneconomic solution. What is needed are wide area technologies that can handle the bursty internetworking traffic efficiently and economically. We will see in the next section that suitable technologies have emerged. A measure of the burstiness of a traffic source is often given as the peak to average ratio. This is a measure of the difference between the maximum instantaneous data transfer rate and the average. The higher the ratio, the more bursty the traffic. We will now take a look at wide area networking. We will look specifically at the technologies used for data communications. We will also look at how suitable each technology is for the carriage of bursty internetworking traffic. A wide area network, or WAN, is a national or international network that supplies communication channels between geographically dispersed locations. The wide area is where most of a company's annual communications budget is spent. As a rough estimate, approximately 70 to 80% of the annual spend of a WAN is spent with service provider companies. LAN traffic regularly achieves speeds of up to 100 megabits per second, but when connecting into a WAN system, which WAN protocol should I use, and what data throughput do I need? Different types of data may require different WAN systems. LAN traffic is bursty and high speed, but can tolerate network delays. File transfers are constant traffic and can also tolerate network delays. Voice traffic is real-time and can't tolerate network delays. And video conferencing traffic is usually about 128 kilobits per second to 384 kilobits per second and is also real-time and can't tolerate network delays. Different technologies can be used depending on traffic type. Possible technologies are PSTN and ISDN dial, leased line circuits, public packet switched networks, or even the Internet. The earliest wide area data networks were built using modems. In these networks, all communication was under the control of the central computer. System Network Architecture, SNA, from IBM, was the most prolific example of this type of network. These were used extensively by large financial, transportation, and industrial organizations from the 1970s, even up to the present day. User devices, most often dumb terminals, were connected to the computer via communication controllers. These came in two types. Front-end processors, FEPs, located with the host computer, controlled communication to all user devices, whilst cluster controllers control access from multiple user devices to the communication link. In most of these networks, a process known as polling was used. The FEP would poll each cluster controller in turn to see if they had information to send. If they did, the information would be exchanged. If not, the FEP would proceed to the next cluster controller. Polling allowed the creation of what are called point-to-multipoint or multi-drop links. In this environment, cluster controllers could be daisy-chained together via multi-port modems. As only one device could send at a time, when it is polled, there would be no conflict. The communication between the FEP and cluster controller was also, due to the polling process, only half duplex, i.e. only one end could be sending at a time. These polled networks have two major drawbacks. Firstly, it is inefficient use of the communications media, and secondly, if the FEP fails, all communication stops. As transfer rates of data in computer networks increased, customers began to need faster and faster links. These could not be achieved using modems. To meet this requirement, service providers began to supply circuits of higher capacity between locations. These have become known as private circuits or leased lines, as the company pays a fixed rate for the line under contract. During the 1980s and 1990s, companies have used leased lines to build private networks that interconnect their locations. Often these networks have been designed to carry both intra-company voice and data. To achieve this, companies have deployed communication equipment known as multiplexers. A multiplexer, or MUX, is a device that can take traffic from various sources and combine them onto single or multiple data links to another location over a common line. There are basically two types of digital multiplexing: time division multiplexing, TDM, and statistical time division multiplexing, STDM. Up until today, most companies have been happy to build private networks around leased circuits of up to 2 megabits per second E1 rates. These were used to carry voice, host terminal, and some LAN-to-LAN traffic. However, the increased internetworking of routers has seen significant growth in bursty LAN traffic. This has resulted in an increase in use of other WAN technologies more suited to transporting this type of traffic. A multiplexer takes data from a number of the attached devices and combines or muxes them onto a high-speed data link. The speed at which the line operates, the bits per second, must be greater than the sum of the individual terminal speeds. The trunk capacity is chopped up into a number of fixed capacity time slots. On most TDMs, this is normally 64 kilobits per second, equal to one voice channel. Normally, the devices attached to the multiplexer can only connect to a single device at the remote end. However, they allow any type of data to be carried: voice, video, real-time applications, and data applications. Response times can be defined in the network and are independent of network loading. They are, however, not efficient at transmitting bursty LAN internetworking traffic. The more time slots allocated to a particular input source, the higher the effective transfer rate and the more information that can be sent. This allocation is, however, fixed at configuration time and can only be changed by reprogramming the multiplexer. Typically, it only operates at speeds up to 2 megabits per second. Some TDMs available on the commercial market will work at higher rates, but there are few that will work with optical networks. TDMs are considered wasteful of bandwidth. Because of the time slot technique, when a channel is idle, that time slot is idle and therefore wasted. This is not efficient with bursty LAN internetworking traffic. To transmit this type of traffic, the amount of bandwidth allocated will be the peak transfer rate, not the average, hence wasting significant expensive trunk capacity. STDM, or statistical multiplexing, as people sometimes call it, is simply another form of TDM. STDM will only reserve bandwidth on the data link when a device is being used. If a device is idle, the STDM will not reserve bandwidth, making it available for other users. Therefore, STDM is very efficient. It does what seems like pouring 2 liters into a liter glass. With this method of multiplexing, the sum of the individual terminal speeds can exceed the speed of the data link. It achieves this by using buffers and software processors to control trunk bandwidth allocation. STDM cannot transmit real-time data, as the delays in an STDM network are not fixed. Hence, they are not suitable for the transmission of voice traffic. STDM systems normally have speed limitations of below 2 megabits per second. Terminals do not transmit all the time, and terminals connected to the multiplexer rarely work simultaneously. So a statistical multiplexer only transmits data over the data link when a terminal has data to send. Traditional statistical multiplexers are now being replaced with new technology that can provide all the benefits of statistical multiplexing, but at higher speeds. Both frame relay and ATM, to be discussed next, provide statistical multiplexing, but can operate at much higher speeds. In circuit switching, a dedicated communications channel is established between the two end systems. A voice call on the telephone network is a good example of a circuit-switched connection. In circuit switching, there is always a mechanism to establish and release the end-to-end connection before and after information is exchanged. This is called the call setup. Circuit switching has been used for many years on the analog network with modems. However, recently there have been circuit switching services based on digital networks. Originally available in Scandinavia and America, these early networks have been replaced, at least in Europe, with the Integrated Services Digital Network, ISDN. More of that later. Switched circuits can be used to supplement a dedicated leased line. For example, an appropriate bridge or router may use a dial-on-demand protocol to automatically dial a switched line if the traffic on the dedicated line exceeds its capacity. It may also automatically dial a connection should it detect the leased line has failed. Switched circuits are also used to perform occasional data transfer between remote offices. A switched circuit might connect every 15 minutes to transfer the latest batch of electronic mail. Integrated Digital Services Network, or ISDN, is Europe's most common form of circuit switching used for voice, video, and data transport. ISDN is a completely digital connection between users. In ISDN, there are two types of channel. A bearer, or B channel, which is the basic information channel and is always at 64 kilobits per second, and a D channel, which is most often used as a signaling channel. The D channel will support a signaling system like Q931. There are two ISDN services available to customers. Basic Rate Access, or BRI, which gives an access of two B channels and one 16 kilobits per second D channel, with a total customer usable transmission rate of 144 kilobits per second, which is multiplexed over a physical 192 kilobits per second interface. The additional 48 kilobits per second is used for various framing and synchronization purposes and is not available to the user. B channels in the BRI can be used to carry either voice or data. The BRI is aimed at the small business, home workers, and heavy internet users. The second is Primary Rate Access, or PRI, using an E1 link with a total transmission rate of 2.048 megabits per second. Normally this consists of 30 B and 1 D channels, all of 64 kilobits per second. The remaining bandwidth is used for framing and synchronization purposes. Most commercial ISDN PRI services can be configured to support a variable number of operational B channels up to a maximum of 30. This flexibility allows the service to be aimed at a full range of medium to large office sizes. ISDN has been particularly successful in Germany, France and Scandinavia, where it is tariffed competitively against normal analog and low-speed leased lines. ISDN has been used for small office, home office, SOHO interconnection, LAN interconnection and video conferencing. It is also used to provide bandwidth on demand and link failure backup. In both these modes, the flexibility provided by the ability to signal a connection is of great significance. There are two basic types of networks: connection-oriented and connectionless. In a connection-oriented network, a path between 2 points must be established before information can be exchanged. Once a path has been established, all the information will follow the same path. A connection in the network is called a circuit. These circuits can either be physical connections, such as in the voice or TDM environment, or virtual, as in X25, frame relay, or ATM. Circuits can also be permanent or switched. Permanent circuits, real or virtual, are pre-established. Typical examples of such are leased lines or permanent virtual circuits in frame relay, PVC. Switched circuits, real or virtual, are dynamic and need to have a setup sequence, dialing a telephone number, information transfer, conversation, and close down, replacing the handset. A connectionless network can pass the packet of data through any path within the network. The packet, or frame of data, is called a datagram. IP used in the Internet is a connectionless network. These are very much like the letters in the postal service. Each has an address of the destination. Once posted, the actual path taken to deliver the envelope may vary. There is no pre-configured path down which the IP datagrams will flow. This will depend on the actual situation of the individual networking devices and links when the datagram arrives to be forwarded. So what first is a packet? The term packet generally refers to a package of data exchanged between two devices over a communications link. Packets can therefore occur at different layers in the OSI model. For example, an IP datagram is a network layer packet. Similarly, a frame relay frame at the data link layer can also be considered a packet. And just to confuse even more, a cell in ATM can be considered a packet of fixed length. The thing all these packets have in common is that the information is contained in a discrete package, which also contains control and routing information to assist in the package's delivery. Packet switching is a technique for transmitting packets of information through multiple linked networks. Packets make the trip through the switched network in hops. If computer A needs to send a packet to computer Z, the packet first travels to R1. R1 stores the packet, retrieves the address information, and looks this up in a routing forwarding table, route lookup. In this example, it determines that the port to R2 is the best path. It is clear that a router network is a packet switching network. One interesting aspect of packet switched networks is the ability to emulate circuits within the network. This gives the appearance of a straight-through wire from one location to the other that provides faster delivery and better service. A virtual circuit is a permanent or switched path through a packet switched network that is set up for a specific end user or application to use. X25, frame relay, and ATM networks provide virtual circuit services. Virtual circuits eliminate the overhead of a full route lookup, which could be substantial. Normally, a virtual circuit can be identified with a very small indicator. In addition, it is possible to specify a specific transfer rate to a virtual circuit, which is not possible in a datagram network. These advantages often outweigh the additional administration overhead associated with virtual circuits. A virtual circuit is a dedicated point-to-point communications line between two end stations on a packet-switched network. It provides a temporary or dedicated connection-oriented link or path through a switch-connected network. Devices along the circuit are programmed with circuit numbers, so that when packets arrive, the switch knows exactly how to forward them without the need to examine the packet header in detail. This predefined path improves performance and reduces the header size of the frame or packet, thus improving throughput as well. Technically, the underlying physical paths through the packet switching network may change to avoid congestion or downed lines, but the two end stations maintain a connection and update the path specification as necessary. On the access link to a packet switched network, a user can now define multiple virtual circuits, one to each of his other endpoints in the network. This allows him to provide a virtual, fully meshed network from only one physical connection. Virtual circuits are best when large amounts of traffic are anticipated between two endpoints on a regular basis. They also have the advantage of adding order to the design of networks, as information flows can be controlled. Virtual circuits allow the definition of throughput to be defined for a particular flow, and with ATM, further parameters are added to define delay characteristics. The circuit is called virtual, as unlike circuits in a circuit switching environment, no resources are allocated to the circuit. Remember that packet switching networks are statistical multiplexing environments. There are two types of virtual circuits, permanent and switched. A permanent virtual circuit is usually provisioned by the service provider as part of the user's contract, whilst switched virtual circuits are signaled on demand by the user as and when he needs connections. X25 is the best known packet switching technique and was designed for the 70s analog market and does not perform as well with late 90s digital links. A packet switch network is called a packet switch digital network, PSDN. Packet switching networks are worldwide. These are available in nearly every country in the world. Specifically designed to operate over error-prone analog lines, it supports extremely good error detection and correction systems. The standard is well defined by the International Telecommunications Union, ITU, and as a communications protocol, it operates at the physical data link and network layers of the OSI model. X25 is a connection-oriented protocol and can connect more than one session over the same link using virtual circuits. It supports both PVC and SVC connections. As a packet switching technology, it supports statistical multiplexing. X25 has lots of features due to being a mature networking technology. Speed is normally 9.6 kilobits per second to 64 kilobits per second, but it can support higher speeds. France Telecom and Deutsche Telekom both operate up to 2 megabits per second. Users can connect to the PSDN via the ISDN, PSTN with a modem, or leased lines. Although packet switching is one of the biggest WAN technologies supported by major PTOs, the current installation base of new packet switching equipment has been declining over the last few years. Frame relay was developed in the early 90s as a solution for the transport of bursty LAN internetworking traffic. Frame relay is another connection-oriented networking method, similar in operation to X25, but much simpler and faster, and better for bursty LAN internetworking applications than X25. Frame relay is a high-performance WAN protocol that operates at the physical and data link layers of the OSI model. It is an example of packet switching technology enabling end systems, in other words computers, to dynamically share the network medium and the available bandwidth. Variable length frames are used for efficient and flexible transfer. Frame relay specifically supports methods of handling bursty LAN internetworking traffic. For each customer circuit, an amount of bandwidth can be defined that will always be delivered. This would be close to the average transfer rate of the user. A burst level is then defined into which the user can burst. The network will attempt to deliver this data if capacity is available. Because the user pays less for the burst capacity, the overall network is cheaper than an equivalent leased line solution. Frame relay also supports virtual circuits to provide logical meshing of users over a single network access. As frame relay is a significantly simpler protocol than X25, it is able to work at much faster rates. Typical frame relay access rates are between 64 kilobits per second and 2 megabits per second, but it can operate at higher rates. ATM is a high-speed network technology that is designed for both LAN and WAN, although its use in LANs has been slow to take off. It is connection-oriented switching technology, meaning that a dedicated circuit is set up between end stations before a communication session can begin. All traffic is transmitted in fixed-length cells, as opposed to variable-length packets in X25 and frame relay. Although the transport of information is in cells, the basic techniques of ATM are similar to other forms of packet switching. This difference between fixed and variable length is critical to what ATM offers. Picture a busy intersection on a motorway. A large lorry is attempting to negotiate a sharp turn. All the rest of the traffic in the intersection is held up while this happens. Now picture the same intersection where all the vehicles are sports cars. In the latter case, traffic flows smoothly, even predictably, because there is no delay caused by big trucks. This ability to control the delay of traffic allows ATM to support different levels of service. With X25 and frame relay, the network can only control the throughput of traffic. With ATM, the network is also able to control the delay and variation in delay of user traffic. It has sophisticated mechanisms to manage the throughput and delay experienced by different traffic types. This allows ATM not only to carry data traffic, but also delay-sensitive multimedia traffic like voice and video. ATM is a very high-performance WAN protocol that operates at the physical and data link layers of the OSI model. It is an example of cell switching technology, which is a special form of packet switching. Like X25 and frame relay, ATM is connection-oriented, can support logical virtual circuit network connections, allowing multiple traffic sources to dynamically share network resources and provide statistical multiplexing. Because ATM switches fixed-length cells, most of the information switching can take place in hardware. This means that ATM works much faster than the software-based switching method used by X25 and frame relay. Hence, ATM networks are able to operate at far higher speeds. There is no one technology that is right for all applications. Complex network architectures will generally be put together using a number of different complementary technologies. Generally, the two critical deciding factors that need to be considered are the transfer rate required and the number of locations to be interconnected. Generally, leased lines are best when the number of locations to be interconnected is small. If the number is larger than, say, 5, then a switch service should be considered, where the ability to use virtual connections over a single network access should make the overall network cost cheaper. We need then to look at the required transfer rates of all the application traffic to be carried. ISDN and X25 are limited to the lower speeds, mainly in the n times 64 kilobits per second range. Both also may have efficiency issues if a large amount of bursty LAN traffic is to be carried. Frame relay is ideal for customers requiring multiple site interconnection, with transfer rates of between 64 kilobits per second and 2 megabits per second. Above these rates, ATM should be considered. Remember that frame relay can be interworked with ATM, providing a seamless solution from 64 kilobits per second up to multi-megabits per second. Thank you for taking the basic data communications training module. We hope that you have now understood some of the basics behind the rapidly emerging world of data communications. Thank you for your time.